Alright, so in this video we're going to go ahead and talk about another algorithm that we can use to search for paths in our graph, and this algorithm is called the Bellman Ford algorithm. Okay, this is going to be another version of a single source algorithm. So basically we start at a specific node on the graph, and then we can go ahead and find the distance to any of the other nodes on the graph from that source node. It's a very similar algorithm to what we saw with Dijkstra's, except we're going to see that the Bellman-Ford algorithm actually goes ahead and fixes one critical flaw that we had with the Dijkstra algorithm. And that flaw is the fact that Dijkstra's algorithms do not work when we have negative weight edges somewhere on the graph, right? We're going to take a look at why that is a critical problem here and how Dijkstra's doesn't really handle that. So let's just say we have a graph that looks something similar to this. You can see we have our directed edges here, and we can see it's pretty much everything we would normally expect to see in a graph, except you can see one of the edge weights is actually negative here. All right, so we can see to go from 1 to 2, it's going to cost 12. To go from 1 to 3 or 1 to 4, it's going to cost 3. And to go from 2 to 4, it's actually going to cost negative 10. Right, and what we're going to see here in a minute is how Dijkstra's is going to end up not giving us the correct overall costs to go from a specific node to any of the other nodes in the graph. All right, so what we're going to do is we're just going to quickly walk through what Dijkstra's algorithm would look like on this particular graph, and we're going to see what goes wrong. All right, so let's just say we're going to go ahead and find all of the distances from node 1 to all of the other nodes in the graph. Right, so in typical Dijkstra fashion, we start at node 1. The distance from the node to itself is always going to be 0, so we mark it as visited and give it a weight of 0. And then at that point, we go ahead and we try to enumerate all of the adjacent nodes to 1, right, which is going to end up being nodes 2 and nodes 4. Right, so after we discover them, we can go ahead and update the total costs to get to them as we normally would. So we know because they are directly adjacent, we can get to node 2 with a cost of 12, and we can get to node 4 by a cost of 3. Right? And because this is Dijkstra's and this is a greedy algorithm, we're just going to, excuse me, going to go ahead and grab the lowest cost edge out of all of the adjacent edges to the node we're currently on, which is node 1. Right, so the lowest cost edge is of course going to be the edge going to node 4, which has a cost of 3. So we go ahead, we visit node 4, mark it as visited, kind of lock in that weight for now, and then we go ahead and we check to see what nodes are actually adjacent to node 4, which in this case is only going to be node 5. Right, so we can go ahead and update the total cost and the total cost it gets to go from node 1 to node 5 via node 4, right? And that total cost is going to end up being 5, right? So after we do that little calculation, there's no other nodes adjacent to 4. We pick the next lowest edge, which is adjacent to the current node we're currently on, which is node 4. So we go ahead and we lock in node 5. Node 5 has no adjacent edges, so we're done there. And we're going to end up falling back to taking our next cheapest edge, which is, of course, the edge between 1 and 2, right? So we visit node 2, and then, in accordance with Dijkstra's, we check all of the nodes that are adjacent to node 2, and we look to see, can we find a better path to any of the other nodes we've already visited by going through node 2, right? Which actually, in this case, we're going to find one of those paths, right? Because this edge from node 2 to node 4 actually has a negative weight associated with it. So that means we can go from node 1 to node 4 by going through node 2 at a cheaper cost than just going from node 1 to node 4, right? Because if we go down this path, we are going to actually go negative. Right, so to go from node 1 to node 2 costs 12, but then to go from node 2 to node 4, we subtract 10 away from whatever the total cost would be. So to we can actually reach node 4 with a total cost of 2 instead of a total cost of 3, which reduces that overall cost to get there. But we're going to run into a problem now, right? We have now visited all of the nodes, marked them all as done. So that means our algorithm is actually going to just kind of exit there and quit. But we did not actually get to update the rest of the nodes that might be adjacent to node 4, which is the node we just found the cheaper cost to. Right? If we look here, the total wait to get to node 5 is actually incorrect in this instance then. Right? If we can get to node 4 with a cost of 2, then getting to node 5 should actually only cost us 4. Right? Because Dijkstra's is greedy in this instance, and the fact that we stop as soon as we have visited each node once results in the fact that we may actually get incorrect answers out of Dijkstra's algorithm in these instances. Right? This isn't going to necessarily happen every time, but what this just basically means is that when we run Dijkstra's algorithm on a graph that has negative edge weights, we may actually get a non-deterministic answer, right? Just because of how everything is structured, right? We won't deterministically get the correct answer every time, right? So to fix that, we actually end up with the Bellman Ford algorithm. Okay, and the Bellman Ford algorithm is actually designed to be able to handle the cases where we have negative edges. However, we're going to handle these cases at basically the cost of some efficiency, right? In its simplest terms, Bellman Ford is virtually identical to Dijkstra's, with the added case that we are basically going to be running Dijkstra's multiple times over and over again, exhaustively searching every single node and updating all of the paths as much as possible. This is actually in a manner, very similar to what we see with the with the all points shortest path algorithm that we discussed, where we look at every single node and find the cost between every single node to every other single node in the graph. We do it in a fashion kind of like that almost. Basically, with the Bellman Ford, what we're going to end up doing is running Dijkstra's at least once for every single node in the graph, right? So it's going to just reiterate over itself multiple times until we have visited every node multiple times, which enumerates all of the possible negative edges to allow us to account for those shorter paths that might be there. All right, so what we have here is basically I have the Bellman Ford pseudocode, or a good chunk of the pseudocode for Bellman Ford on the left-hand side, and on the right-hand side we have Dijkstra's pseudocode. Okay, and the bold bit right down here is really the heart and soul of Dijkstra's as we know it. Right, so for each vertex, we go to each adjacent node, see if it's visited, check what its total cost is to get there, see if we can update our total costs in any way if we found a shorter path, etc., etc. Okay, what we're going to notice is that on the left-hand side, again, with the bold stuff right there, those two pieces of pseudocode are exactly alike. There's no difference between them at all. The only difference is really the overall containing for loop or loops that specify exactly how many times the algorithm is going to run. Right, so in our Dijkstra's algorithm, we basically have while our queue is not empty, while there are nodes that we have not visited yet, we're going to run the algorithm. And then of course down here, we also have a couple conditional checks to see whether we've actually visited the node that's in the queue already. Whereas on the left-hand side, in the Bellman Ford pseudocode, we basically have a for loop that says for every single node in the graph, we're going to go ahead and rerun our overall algorithm again. Right? So we're basically running Dijkstra's algorithm multiple times in order to get the achieved result. Now, I had mentioned that this is only a good chunk of the pseudocode. There is actually a secondary part that we'll talk about in just a minute after we walk through the algorithm. right? Bellman Ford is effectively going to have two parts to it. We have the first part, which enumerates all of the lowest cost edges and accounts for all the negative weights that may or may not be in the graph. And then we have a second part, which is going to check for something that's known as a negative cost cycle, which we'll see in a minute, and we'll see why that's bad. Because if we end up with one of these negative edge weight cycles, then we basically cannot actually find the shortest path from the start node to the other nodes in the graph. And we'll see why that is in a second. Okay, so again, we're just going to kind of walk through how Bellman Ford works and how it actually takes these negative edges into account. All right, so we're starting with the same graph that we had before. Again, we have the negative edge weight right there. And basically what we're going to do is we're going to go ahead and pick our node. In this case, I think we're starting from node 1. And we, again, just as we normally would in Dijkstra's, enumerate all of the weights or all of the adjacent nodes to the edge we started from, which is 1. Right? So we can see that the cost to get from 1 to 2 is 12, the cost to get from 1 to 4 is 3, etc. But now, this time, instead of coming back around to the top of the algorithm and picking the lowest cost weight, what we're going to do is we're just going to move on to the next node in the graph. All right, so instead of necessarily picking this edge 1 to 4 and going to node 4 and visiting all of its adjacent nodes, we're just going to iterate through all of the nodes in the graph in sequential manner. So we're going to end up taking node 2 here, for instance, next. And what we're going to end up doing now is visiting all of the nodes that are adjacent to node 2, right? Which, as we can see here, node 2 is adjacent to node 4, and we can go ahead and update that current weight to get from node 1 to node 4 via node 2 right off the bat. So when we do that, we can see we lower the total cost to get to node 4. After we've lowered that cost, we then go to and move on to the next node in the list, which is going to be node 4. And from node 4, we can go ahead and update the total weight that we had before, or the total weight to get from node 1 to node 5 via node 2 and node 4, which gives us a total weight of 4 overall. Right, so we just, instead of going and looking to see what edge has the lowest weight and then pushing that edge onto a queue, we remove the queue aspect from this one, and we just iterate over all of the nodes, performing the same Dijkstra type operations that we had before. So pick a node, enumerate all of the weights, update all of the weights to get to the adjacent nodes, see if there's a better path by going through another node, etc., and then move on to the next node. And this just happens over and over and over again until we end up enumerating all of the weights and allowing us to update and account for these negative edges. Okay. What I had also mentioned was that we also have one more step that we need to perform in order to make sure that we don't end up with one of these negative cycles. But first, let's see why one of these negative cycles is actually kind of a bad thing for us. So again, we have a very similar graph. I just kind of flip-flopped some of the directedness of this. So for instance, node 5 is now pointing to node 4, etc. And what we're going to do is we're going to start from node 5, and we're just going to kind of do a very general figuring out of the weights to go from node 5 to any of the other nodes in the graph, just by kind of looking at this. We're not going to use a specific algorithm. We're just going to kind of look at it and walk through it. Right, so we know the weight to go from node 5 to node 4 is going to be 2, right? Because that's the weight of that edge. After that, we want to find the weight to go from node 5 to node 1, right? Which is, of course, going to be 5, right? Because we have an edge weight of 2, we have an edge weight of 3, 3 plus 2 is 5. And then the cost to go from node 5 to node 2 is going to have to go to 4, going to have to go to 1, and then we end up at 2, right? which gives us a total cost of 9. Now, the big question is, can we find a cheaper route to go to node 4 from any of the other, or to go from node 5 to node 4 in some other way, right? Which, because of this negative 10 weight right here, we actually can do. Or we actually can, right? So if we go and take this negative 10 edge right here, what we end up with is we get an actual negative cost, or an actual cost of -1 to go from node 5 to node 4 if we take this cycle, right? So that makes it cheaper. But now we have to ask the same question. If we update this edge, or the cost to get to this node, we also have to see if we can update the weights to all of these other nodes, right? Which, again, we actually can, because we actually have this cycle in the graph, right? So if we take this negative 10 edge, which gets us a negative cost of -1, that means we have to update the cost to get to 2, or to get to node 1, which gives us a cost of 2, which means we have to update the cost to get to this other node, which drops that down to 6. And then we can go ahead and take the negative edge again, which drops that edge down to -4. And this is just going to keep going on over and over and over again. And what we end up with is basically this infinite cycle where our algorithm could not actually ever terminate, because it's just going to continually get a lower and lower cost every single time we iterate over this cycle in the graph, right? So that means our algorithm has no chance to actually terminate or stop. It's just going to keep going over and over and over again. So to account for that, our algorithm is going to need to be able to check for these negative weight cycles, which is what this last little bit of pseudocode actually does here. Right, if we check out the pseudocode, basically what we're going to do is, one more time, we're going to end up iterating over all of the nodes in our graph so far, and we're going to take the newly discovered weights, and we're basically going to check to see if we can end up with one of these cycles. And the pseudocode may not describe it very well, but hopefully visualizing it, we can kind of look at, or we can kind of see what's going on a little bit better. So effectively, what the pseudocode is doing is we're going to start at our start node, and we're really going to take the total cost to get to the current node we're on, plus the cost of the edge to the adjacent node, and see if the total cost to get to that, if the total cost of the two things we just added up together is less than the total cost to get to that node, right? So for instance, in this first case, we're looking to see if the total cost to get to node 5, which, because it is our starting point, is 0, plus the cost of the edge to get to its adjacent node 4 is less than the total weight we have to get to node 4, right? So 0 plus 2 is not less than 2, therefore we do not know of any cycles yet, right? Then we can move on to node 4. And what we're checking here again is the total cost to get to node 4 is 2, right? So we take 2 plus 3, is that less than 5? No, it's not, therefore we have not found a negative cycle yet. We move on to node 1. We take the cost to get to node 1, which is 5, plus the cost of the edge to get to its adjacent node, which is 4. Check to see if that's less than 9, which it's not, so no cycles have been found yet. But now, when we get to node 2, we end up taking the total cost to get there, which is 9, plus our negative 10, which is actually going to be less than 2. So because that hits, what we end up with is that is our sign that we have a negative cost cycle, or a negative weight cycle. Therefore, if we find that, we cannot actually say we have, or we can run our algorithm correctly on this graph. Therefore, if you run into one of these cases, you just kind of are going to have to throw an error and quit out and alert the user that says, hey, we have a negative weight cycle. Therefore, we cannot find the shortest path to go from our start node to all of the other nodes in the graph. Because we found this, that means the algorithm will just basically continue running forever, which is not good for anyone. All right. So really, that is all there is to the Bellman Ford algorithm. We're not really going to have any assignments dealing over this algorithm, but it's one of those, if you want to code it up, I would highly recommend it. Just another good algorithm to have, and also gives you extra practice working with the graph data structures we've worked with so far. And with that, that's all I have for this video, so we'll see you in the next one.